Hey everyone, welcome to our COGS 189 BCI project presentation. My name is Shaquille, representing our group, Team One Forever. And while we're at it, let us take a moment to mention the lovely men who worked on this project. Alejandro Panduro, David Liao, Miguel Ramos, Joshua Chong, and Jeffrey Liu. Now I'm going to run you through a little about how we came up with our project. So let's get started. According to a 2010 study by the U.S. Department of Education, 15 to 20% of the population has a learning impairment. That is roughly 65 million people, and it doesn't include those without a medical diagnosis. Such learning disabilities include dyslexia, visual perceptual deficits, or even motor deficits. And most of these disabilities accompany attention disorders like ADD or ADHD. And a problem is that attention plays a big role in learning. So how can we train attention to assist people with these learning disabilities? For our project, we made an attempt to train attention by creating a game that utilizes the attention scale on the NeuroSky headset. We are focusing on attention because we believe that is an essential part in learning. To measure the attention level, we got our hands on the NeuroSky headset to record EEG data. And after getting both ends to work, we combined the two together for our final product, Triton Rush. Moving on to the related works, let's first define what attention is. It is the behavioral and cognitive process of selectively concentrating on a discrete aspect of information, whether deemed subjective or objective, while ignoring other perceivable information. According to Stephen Grossberg, a cognitive scientist from Boston University, attention is important for learning. This is due to the top-down information processing that our brain uses. Top-down processing happens when we work from the general to the specific. In order for top-down processing to occur, attention is required. It includes the ability to notice incoming stimuli, filter based on multiple perceptions, and to finally react to the stimuli.
Further, in the paper Reaction Time, Intelligence, and Attention, Carlson et al. Argue that reaction is related to attention because when attention increases, reaction to stimuli not related to what you're focusing on decreases. This is related to the study EEG Potential Predict Upcoming Emergency During Simulated Driving that we read in class. In the study, they tested the reaction time it takes for a person to step on the brakes when driving a car. However, in our study, we changed up the task from driving to playing a video game. This was done because it has been found that expert video game players often outperform non-players on measures of basic attention and performance. In Bu et al., they argued that playing video games improves a variety of visual and attentional skills. Jimenez also argues that learning requires attention to the relevant stimuli. This might mean that playing video games allows people to improve their attention to the task they are doing. Therefore, by creating a game focused on attention, we hope it helps players improve their attention and eventually improve their learning. There are existing games in the market with the same objective. The NeuroPlus headset is very similar to the game we made because it records attention when playing a game. There are also other games that are solely based on attention and require a motor response, like Catch the Ladybug on the right-hand side that interacts with the user through clicking of a button.
Moving on to the methods. First, we utilized the Google Chrome game T-Rex Rush as a baseline for our application. We found and accessed the GitHub repository for the game, shout out to Shivam Shekhar, the creator, and realized that it was coded mainly in Python. Then we proceeded to clone the code into our own local repository, and then took time to understand the obstacles, variables, environment, and gameplay aspects of the code. Let's quickly reiterate how the game works. The user takes form of a dinosaur running down a path. As cacti appear, the player must avoid these obstacles, mainly by pressing spacebar to make the dinosaur jump. If the player hits the obstacle, then the dinosaur stops and the game is over. Once the dinosaur reaches a certain distance, other obstacles, such as pterodactyls, appear and force the player to purposely not jump. This ensures that the player stays focused and doesn't just hold down the jump button. After understanding the base code of the game, we worked to change the avatars and layout of the game to aesthetically fit our project theme. The picture you see on the screen represents an initial iteration of our game when we attempted to replace the dinosaur avatar with the ninja. In addition, we've placed the repositories of both the base game and our own version in case any of you want to check it out. So, the main difference in functionality between our game and the base game was the method of jumping. To implement this, we continuously measured a player's attention using a NeuroSky headset. First, we would connect the headset to our computers via Bluetooth and confirm the COM port. This would allow us to certify the MindWave mobile program was connected. Then, we would continuously retrieve the user's attention every few milliseconds. If the attention was greater than a certain threshold, we arbitrarily set ours at 45, then the dinosaur would jump. In order to actually record each player's attention, we utilized a library called NeuroPy. While we could have used the SDK developer tools provided by class, we ultimately decided to stick with NeuroPy because it was created specifically for Python, the language our game was programmed in. If we were to utilize SDK, which was coded in the C language, there would potentially be compatibility issues in connecting and recording data from the headset. However, that's not to say there weren't any problems with our code. We struggled intensively with collecting the data and realized after a while that NeuroPy was incompatible with Python 3.0 and above. To work around this, we created an active Anaconda and Python 2 environment to run our program. Finally, the game worked.
But now that we had the game up and running, we needed to go out and find participants. We decided to try the game out with the individuals who we felt would be the most accessible and willing to lend their time. As it turned out, the participants ended up being all males and aged between 18 and 25, with no disabilities. We took note of all the studies performed in the papers we read throughout the quarter and proceeded to conduct our study in a similar fashion. Our experiment dealt with two groups, a control group and an experimental group. For the control group, we had participants sit down and read an article while we measured their attention levels throughout this time using the NeuroSky headset. We explained the function and purpose of using the headset to the participants. We had a separate group of individuals sit down and play the game for 2 minutes while also being connected to the NeuroSky headset. For these participants, we tried to give them tips we noted when playing the game as to how they can try to control their attention level to have a successful run in the game. Some of these tips involved having the participants think of specific tasks, focusing in on specific words, or thinking of math problems to increase their attention level. We also advised them to think of random nouns for trying to decrease their attention level in their game. The data recorded from both of these groups was then transferred into a CSV file, as this proved to be the easiest file type to work with. After we gathered data from both groups, we began to do data analysis. We chose to use Jupyter Notebook as it was the most convenient for us, as we have used it in many of our classes, and since we had to set up a Python environment for the game, it made more sense to do the data analysis using Python.
On to our results. Now that our game is complete and working, we wanted to replace our hypothetical threshold of 45 that was mentioned earlier. In order to find a general baseline of attention for the average person, we decided that we needed to collect data to find the optimal jump threshold. From our data collection, we had 8 participants read an article for 2 minutes. Note, all participants read the same article. During that 2-minute time frame, we were able to gather around 120 data points of attention from each of our participants. As you can see in this graph, each line represents each participant's recorded attention level over the course of those 2 minutes reading the same article. Due to the variability of our recorded attention, we decided to try and normalize the data by grouping 10 data points together and getting the means of those groups of 10. also known as low-pass filtering. This is a graph of the participants' attention normalized. As you can see, in this example of participants 4's raw data and normalized data, the normalized data is easier to visualize. However, it is still difficult to pinpoint a threshold. So we decided to take the mean of each participant's session. In this graph, you can see the mean of each respective participant's attention during our session. From this data, we discovered that the overall mean of our 8 participants was 51.147575. So we decided to set our jump threshold to that value. Because the MindWave Mobile only used whole numbers, we decided to round down and set the threshold to 51.
While our project went well in general, there were a few things that did not work out according to our plan. We originally decided to use Stream SDK and C to gather our data from the MindWave Mobile. However, due to compatibility reasons mentioned earlier, we decided to go with NeuroPy. NeuroPy brought its own set of challenges as we had trouble connecting our MindWave Mobile to NeuroPy. After many hours of debugging, we were able to connect the MindWave Mobile to NeuroPy using COM4. Overall, we learned how difficult it is to actually control attention levels using only one electrode. We also learned how to solve various problems in signal acquisition and filtering, as well as debugging Python code. Finally, we learned about the challenges of real-time BCI and how they apply to our game. With more time, we would have liked to conduct a longitudinal study to see if participants' attention spans would actually increase while playing the game. Because our data on participants playing the game was based only on single trials, each participant had different baselines, and whether or not our hypothesis that the game would improve attention is ultimately inconclusive. And although it isn't tested in this experiment, our long-term objective is to improve learning as a result of increased attention. We would conduct a follow-up study after attention training that would be used to evaluate the effect of these attention increases on learning. As improvements, we would like to implement an additional control in the form of a meditation function in which lower values of attention could contribute to other game mechanics. We hypothesized that being able to switch between attention and meditation could be more valuable in training focus than playing with attention alone. It would also be useful to add multiple lives and have a customizable avatar for more enjoyment. In the end, we want our game to have applications in treating attention deficits such as those found in ADD and ADHD. Even in healthy users, our game can be used to train for better attention and focus to help with everyday tasks such as reading or studying.
And now, here is a short video demonstrating our game in action.